Thank you very much for this introduction. And I would like to thank the organizer for giving me this opportunity to present our work. And so I'll be discussing about this non-trivial Doublon formation in the Quench dynamics of a many-body state, many-body initial state or many particle state which are interacting. And before proceeding further, let me just highlight that this setup or the Quench dynamics of many interacting particles is a topic of paramount interest, and this has been studied in many different contexts, and it gives us many novel phenomena compared to the equilibrium counterpart of these many-body systems. But at the same time, it poses various difficulties in terms of theory and experimental realization. Therefore, there are certain approaches one can study in the Quench dynamics by reducing the number of particles to few particles. So that will be the focus of the talk. So what I'm going to talk today is the dynamics of few interacting particles, not many interacting particles. And this setup is very handy because that gives you less complexities, and also it is easy to access in the experiment, and also it gives us kind of freedom to have some bottom-up approach of this many particle system. And the next thing is this formation of Doublon. Doublon is considered to be the a bound pair of two fermions of different spins. Traditionally, conventionally, this is the definition of Doublon. But any two particle, any constituents, two particles, if they form a repulsively bound pair, then this is also called Doublons. And that has attracted a lot of attention in recent years due to these experiments on cold atoms in optical lattices and so on. And this has been observed in various experiments, not only in cold atoms, but also in photonic systems, superconducting circuits, and all other things. So this will be the focus of our talk. So this, as I mentioned, that this few particle dynamics gives us many insights about this interacting physics. So it all started from this paper of quantum walk, which is the quantum version of random walk, but this is in the context of single particle dynamics. And if you have some particle sitting on a periodic potential with some kinetic energy like J, and if you quench this system, then it evolves like this. This particle will freely move around the lattice sites. Okay, so this is a simple unitary evolution. So there is another version called discrete time quantum walk, but this is called continuous time quantum walk, where this Hamiltonian is time independent, and this is simple our unitary time evolution. Okay, so if you look at this simple simulation here, you start from a single particle sitting at the central site of the lattice, and then you time evolve, you see that this particle moves nicely, depicting this light cone type behavior. And this has been shown to you by Pedram in his talk, and this is one of the experimental observation in cold atoms optical lattice setup. Okay, so this is the density computed using this time evolved states SIT. Okay, so now the question is, if you have more than one particle, then what will be the situation? Then one can incorporate interaction into the system and study this quantum walk, which is again the Quench dynamics of few interacting particles. Quantum walk of two interacting bosons in one dimension, that's the simplest possible case. Okay, so what are the scenarios? So if you start two particles in a single site, that's the initial state, that's the case one I'm going to highlight. The initial state is this. And this can be explained by this famous Bose-Hubbard model, which doesn't require any introduction to this audience. So this, if you quench your initial state with respect to this Hamiltonian, then you can expect two scenarios. One is at small u, and one is at large u. Okay, so this u is the on-site interaction. So what will happen in the limit of weak u? Then these particles, they perform independent particle quantum walk, because they will just behave like free particles, non-interacting particles. But if you go to a very strong interaction, then they will form this effective two particle interaction. So that I'm going to show what exactly it is. So one can consider these diagnostics to see these behaviors. This is the particle density, on-site density, and these are particle-particle correlation in the system. So what happens is that if you have very strong interaction, then these two bosons, they form a effective bound state, and they propagate slowly because now they have a reduced effective hopping in the system. Okay. Okay, so this is the scenario here. You just create some two particle state here, and then if your interaction is 0, then these two particles, they just spread like free particles, and they will reach the boundary very fast. But if your interaction is very strong, then you see the evolution is very slow. Okay, so that's the message here. So very strong interaction, they will make this two particle form a bound state. Okay, so if you look at the two particle correlator, and you see that for weak interaction, there is a free particle dynamics, very nice interference pattern in this correlation. But if they form a bound pair, that is in the limit of very strong interaction, you see that only this central diagonal part are finite, and rest of these correlator elements are all 0. Okay, so this is the experiment done in the group of Greiner, and this is the theory and experiment. I mean, there is a very nice matching of this Doublon formation or repulsively bound pair formation in the lattice. And why do they form a Doublon? I mean, this can be understood from this two particle problem. I mean, this is a very simple argument for this. Suppose you start from this central site where two particles are sitting here, and if this interaction is very large, very strong interaction compared to this hopping, then this, if this one of these particles they comes to the right side, then this energy has to be converted to kinetic energy, which is not resonant with the interaction. Okay, so therefore this particle they prefer to move together rather than splitting apart. Okay, so that's the condition for repulsively bound pair. And if you look at this energy diagram here, you can see that there is a very well-defined bound state band at a very far from the scattering state band. So this gives rise to the gap, and therefore this bound state cannot split into two independent particle states. So this is the reason why this two particle form this repulsively bound pair state, and this has been experimentally observed in the experiment in this paper. Here you can see that if this A0 is this two particle scattering length is 0, which defines the interaction between the boson, then you can see that this pair number slowly decays with respect to the whole time. But if this interaction is very strong, so this is the S-wave scattering length of the order of 100, then you can see that this remains stable up to a longer time. So that's the observation of repulsively bound pair on a Bohr-Savart system. Okay. Now there is another scenario. I mean, here the two particles were sitting on an empty lattice. Suppose you create two particles on an uniform Mott insulator background. Okay, so that's a different scenario. Instead of empty lattice sites everywhere, you just consider one uniform Mott insulator background and then two particles on top of the central site, for example. Okay, so the initial state in this case is this. Again, the same Hamiltonian, Bohr-Savart Hamiltonian, but it is slightly modified because you have a scenario where three particles are sitting in one site. So if three particles are sitting in one site, they may also interact with each other with this three-body type interaction, which is this delta function type interaction. So that means if you have three particles in one site, then this is finite. If not, then this term won't contribute. Okay. So in this case, what will happen? So in our calculation, we try to consider this regime of interaction like repulsive U and attractive W. Because the repulsive W is a trivial case, because if you have both W and U repulsive, then they will trivially form a stronger bound state, three particle bound state, and so on. But the case here is going to be interesting. I am considering attractive U and keeping this U to be two-body repulsion to be very strong. If you can see, this is 10, this hopping is 0.2, that means U is 50 times stronger, and this U over T is 50. So that means very strong interaction. So that means this is necessary. This will make sure that my Mott insular background remains intact, and this extra 2 particles will play the main game here. Okay, so we'll keep this Mott insular background and then vary W to see the behavior. Okay, so here you see, so this part on this left side, W is very small and U is strong as usual, as I said, is 50 times this T. So when W is very small, we see a very nice profile, very slow moving profile, which is the signature of a bound pair state in the dynamics. But as I gradually increase W and make it more and more negative or more and more attractive, then this guy slowly spreads, and then it will spread, and it will show that there is a nice single particle type spreading at the center when W is equals to U. Okay, and then interestingly, if W is increased further, then I come back to my original condition where I see a very narrow or slow moving profile in the dynamics. So this is, yeah. Yeah, it's always ballistic, yes. Yes, yes. It's just, only this effective hopping is getting reduced. So, but the spreading is always there. So here it is, at the center, the spreading is faster compared to this first one and the last one. Because I'm going to show you that this is actually the dynamics of a pair of particles. Here also is the dynamics of pair of particles. The interesting fact here is to see that if I go on increasing W in this direction, I come back to my initial condition here. So here W is 0 or less, here W is much larger than U, but these two conditions are similar. But at the center, I have a free particle dynamics. So that is something we call reentrant dynamics due to two competing interactions here. And these features can be seen from the correlation figure. Here you see the central bright spots, which is the signature of doublons. Here also the signature of doublons, very similar. But at the center we have this nice interference pattern of single particle dynamics. Okay. So how to understand this? So as I said, for W equal to 0 or very small, these two particles which are sitting on top of this, they don't feel that this entire lattice has one particle each or they are free. Okay, so they will just feel that this background is nothing actually, because if this pair moves to this side, it will encounter some interaction, constant interaction if it goes to here. So wherever it goes, it feels the same interaction from the background. So therefore, it is the same repulsively bound pair which was there for the empty lattice side. Okay, so therefore this scenario is very similar to the repulsively bound pair of two particles on an empty lattice. Okay, but if you come here, when U is equal to minus of W, then there this breaking is possible, because if they are together, then the total interaction will be, the total energy of the system will be W plus 3U. But if this is equal, then these two, this particle can go to the other side with the same, the total energy of the system will be similar. So therefore, this pair can, this state can break into this. But here again, when U is much larger, W is much larger than U and attractive, then this particle, that will prefer to stay on top of this and move around on the lattice. Okay, because this energy conservation is not satisfied here. This is the most stable condition. Okay, so this physics can also be understood from the many-body physics of the model. One can still see similar behavior of this pair of particle moving around this background on this background of this, on the foreground of this Mott insulator state from the many-body phase diagram. So then one has to consider this many-body physics of this model. This was actually studied sometimes back in this paper, where they have found this interesting first order phase transition in this optical lattice with a tunable three-body interaction. So they propose how to tune this three-body interaction in their paper in optical lattice experiments, and they showed that there is a first order transition between the Mott lobes. Okay, so what is this? So they said that if W is 0, this is the standard Bose-Hubbard model, and this is the mean field phase diagram of the Bose-Hubbard model. and you have all these Mott insulator lobes, and there are superfluid phases sandwiched between these Mott insulator lobes. Okay, but what they said that if you increase W and make it minus 1.5 times U, then this Mott 2 lobe will vanish completely, and there will be a direct transition from Mott insulator 1 to Mott insulator 3, and this transition they call a first order transition. Okay, so they used this mean field theory analysis, a single site mean field decoupling approximation, and then they substantiated their results using this quantum Monte Carlo simulation in a 2D setup. Okay, so this is what it is. I mean, you directly go from Mott 1 to Mott 3 through this boundary. Okay, so there is no superfluid phase. But in our case, our initial state or state lies somewhere here. So we are interested in some region which is here, just above the Mott insulator 1. So because we are creating 2 extra particles on top of Mott insulator 1, so that means we are here. But here in their paper, they are saying that there is a direct transition. So there is nothing in between. Directly you go from Mott 1 to Mott 3. Okay, so that means if their paper is correct, then our prediction is wrong. So I will show you this prediction is actually not correct to show that our prediction is correct. So that means this result is not true. So there is another phase hidden within these 2 lobes. So that is what is our prediction. So we studied the same model using DMRG for 1D, and this is cluster mean field theory in 2D setup, and we showed that there is no direct transition between Mott 1 and Mott 3. Okay, and rather you find a pair superfluid phase is sandwiched here, and this pair superfluid is actually a pair superfluid of pairs, 2 particle superfluid phase, which is somewhere sitting here. And we confirmed this from our 2D CMFT simulation. There also we found a signature of pair superfluid phase. So that means our initial state, or the state we are considering, or the regime we are considering, is somewhere here, just above this Mott insulator 1 phase. So Mott insulator 1 plus 2 particles. So in this regime, if you go on increasing the chemical potential, so your system will accommodate only 2 particles at a time till it reaches Mott 3. So which was not shown here. Okay, so there was a direct transition from here to there, and we tried to verify our results concretely by comparing it with QMC data, and we found that in the critical regime our result matches pretty well with the QMC data. So these boxes are QMC, and this square is the scaled critical points obtained from our simulation, cluster mean field theory extrapolation. So you can see that near to the critical regime, they actually match very well. But far from, away from the critical regime, or in the limit of dominant hopping, they don't match. That is obvious, because cluster mean field theory works well when your interaction is very strong. Okay, so this is the message. So this means in this regime, you can have actually a signature of pair of particles moving around the lattice. Okay, so that is what we also see in our studies. So this is what this message says, that this 2 added bosons experience uniform MI background, and then they just move freely on top of this MI background, giving rise to this slow dynamics. Okay, so another case here, when these 2 particles are sitting next to each other. Okay, so again another setup. Instead of sitting on top of each other, suppose you start with this initial state when they are sitting next to each other, then what will happen? So in this case, in the limit of strong interaction, they never come on top of each other. Okay, so you cannot form a bound state locally. Okay, if you start with 2 nearest neighbor bosons or non-local bosons and study this quantum work, then you cannot form a local bound state. So that's the thing, because if they are bosons, they fermionize. Okay, in the limit of very strong interaction, they would fermionize, they cannot come on top of each other, there is no overlap of wave function. So therefore you see that there is a very nice, in the limit of strong interaction, they just anti-bunch. Okay, in the correlation you can see this finite matrix elements in the opposite corner of the diagonal. So this is a theory, and this is again the observation by Greiner's group. So in summary, up to this point, you can see that if you have initial state like this, 2 particles in a single site, then you increase the interaction, they form a bound state. There's a very nice central spot here in the correlation matrix. But if they are starting from the nearest neighbor sites, they don't form any bound state in the strong interaction limits. Okay, so they form an edge. Same Hamiltonian. Yes, yeah. Yeah, so now the big question is, can we form an on-site bound pair or doublon from two non-local particles? Okay, so that's the question, because previously I showed that two non-local particles cannot form on-site bound pairs. So the question is, can an on-site pair or doublon of non-local bosons possible in the dynamics? Okay, so to do this, we started with this initial state, which is completely different from the previous initial state, but these are all bosons. Now instead of single species boson, we have two different types of bosons, two component bosons. So we just assign some pseudo spins to distinguish the two components. So blue up and red, up spin and down spin. So these are two different components. And the initial state for this is this. Okay, and this two component, two species Bose-Hubbard model has been studied in different by different groups, and experiments are also there. So now the question is whether we can see some bound state here. Okay. Now this Hamiltonian for this is this. You have two different hoppings for two different components. This is the on-site up-down interaction, and this is the individual intra-species interaction. So since we have two particles of blue type, then we have only one kind of interaction, up-up interaction, and we of course we have up-down interaction because this particle has chance to go to the other side. So here we consider a hopping imbalance in the setup, because we can have different species of particles, so both can have different masses. So therefore this hopping will have different values. So in our numerical simulation, we consider this interaction between blue particles to be very strong, 10, and then we perform this TVD simulation with some L equal to 41. And here we have two competing interaction, U up down and U, and then we expect some novel scenarios. So now you see here U up down is 0. I am just increasing U up down along this direction. In the first figure, you can see that since this U up is very strong, then there is a doublon of two identical particle form, as our previous discussion says. So there, and this light particle is heavier. Suppose I consider that this red particle is heavier. So therefore, the dynamics of this is also slower. So therefore, together they perform a slow dynamics. And as I increase U up down up to 5, this slowly spreads out. But again, at U up down equals to 10, you see something interesting happens. Suddenly you see that a faster dynamics appears unidirectionally. Okay, on the left side there is a faster dynamics. And again, further increase in U up down, you see that you come back to the previous state. Okay, so there is a slower dynamics. So this is again some reentrant feature, but the interesting thing happens here when U up down is equal to 10, which is the value I consider for U. Okay, intraspecies interaction and interspecies interactions are same, then only there is something interesting happening, and what is happening here is the following. If you zoom it in, you see that here the density was 2, which is black here, and this was red, that is 1. That means the left side is 2 blue particle, right side is 1 red particle, and immediately after the dynamics, soon after this, maybe it's a short time dynamics, you see that the right side is becoming completely dark. So this means the density of this right side is becoming 2, and this one extra particle that remains here, it scatters off on the left side as a free particle. So what is happening here is that there is a doublon being formed on the right side, and one extra blue particle scatters off. So we started from this, and in the dynamics, this guy goes here, form a bound state, and this extra particle goes like a single isolated particle. So that is what is happening here, and so this up-up pair breaks and one up-down bound pair is formed. So this is what is non-trivial about it, because in the previous cases I showed that two non-local bosons cannot form a local bound state, but here the non-local bosons actually they form a bound state here in the dynamics due to these two competing interactions. So to quantify these interactions, this phenomena, we computed this probability of Doublon formation, P up down, and up pair formation. Now you can see that when U up down is 0, then you have this up bound state probability is higher compared to this up down. But at this resonance condition, when this is equal to U up down is U up up, then you have a very large probability of Doublon formation, and this up pair completely vanishes, and then again it re-enters. When U increases, you come back to this up bound state. And then we analyze how this probability depends on this hopping imbalance. You can see that when this hopping imbalance is very strong, then we see that this probability of pair formation is maximum. So in the dynamics, you can see that it saturates to a very strong value for stronger hopping imbalance. But when they are having no hopping imbalance, then it's around 50% of probability. Okay, so 50% for this, 50% for the up pair. Okay, so now what happens here is that here when there is no hopping imbalance, these two states have the same energy. So therefore we see 50-50 probability of up bound state and up down bound state. But when this hopping imbalance is introduced, then this guy will have a slower hopping, reduced hopping. Therefore this up down state, this state is more favorable compared to the other state. So this is the non-trivial formation of Doublon. But now if we increase number of particles to this, 2 up and 2 down, then something new happens here. So we get a 3-body bound state, 3-particle bound state, which we call a triplon. So you can see that 3-particle bound state is formed here, and 1 extra particle that moves out in the dynamics. And we get 2 resonance conditions here when one is U up down is 5 and U up down is 10. In this case, a 3-body bound state is formed. In this case, all the possible bound states are probable. Okay, so here is the signature. You can see this up down pair probability up and down. So this is finite, this one is finite, and this one completely vanishes at 5. But here all of them are almost equal to each other. I mean, they are equally probable. So in the time, as a function of time, if you see that this probability is this up down is maximum, and this is somewhere here at 1, and this vanishes. This up completely vanishes. But what happens here at the second resonance at U up down 10, we see a very steady, stable oscillation for all these probabilities. So this we are trying to see why this is happening, because you see, I mean, here the oscillation initially, I mean, this probability shows some oscillation initially, but it damps away. But here there is a very steady oscillation up to a certain point. Okay, so this is the message here. But what I'm going to tell you is that this Doublon formation is stable because we have lattice in space. So since we have free lattice sites available in the system, then this Doublon formation is stable. But if you have no lattice site, no free lattice sites in the system, you just take a double well in your calculation, then you will see that no stable Doublon is formed. So you will always see that there are oscillations. If you compute the probability, then this going to here and coming back. Okay, so both these pairs have the same energy. So therefore, you will have stable oscillation. But if you have free lattice sites around here, if you have extra sites here, once Doublon is formed, this extra particle has the free space to move out. But here it cannot. So it remains here. Therefore, it can hop back and forth between these two sites. So therefore, a stable Doublon cannot be formed. Okay. So you need a longer lattice to see these stable Doublons. Okay. Now possible observations. So how to observe this? The most suitable quantum simulator is ultra-cold bosons in optical lattices. 2-component setups. You have several interactions in the setup in the system. It's a complicated system, but doable with spin-dependent optical lattices. And you can also have dipolar quantum gas, and you can take a ladder geometry, and then you can tune this interspecies interaction by the interaction between the two layers. And but now this NISQ devices or noisy intermediate scale quantum devices are also suitable for this simulation. One can create arbitrary lattices and study this phenomena. But however, you need to transform this two-component Bose-Hubbard model to in a qubit language. So, but we are considering bosons, which are like you cannot transform this to qubits because you have more number of states locally. So then one has to find out a model where this same phenomena can be seen in a setup where operators can be converted to qubits. Okay, so we need a different setup. So we show a similar physics which can be obtained in the context of Hubbard model of two-component systems. Okay, so this is this. Now you, instead of two bosons, two species bosons, you consider two species spinless fermions and two up spins sitting next to each other and one down sitting here. So you have initial state like this, and you allow near neighbor interaction for this species and also up-down interaction between the two species. Okay. Now you do the analysis. So it's a 3-particle initial state, and a stable doublon in this case can also be formed if this resonance condition is achieved. So here there are two interactions, U up-down or U between the up-down particles and V. So when this V is equals to U, then you get this stable doublon in the dynamics. So this model can be easily mapped to a qubit model, and one can simulate this on a quantum device. So this is an ongoing work which is done by my student Vishwajit, which is sitting here. So he's an expert in this. I don't know much about this, but I mean, if you have any queries, you can certainly talk to him. So this is the Hamiltonian of two-component system. This is the Hubbard model. And you can transform this using Jordan-Huygner transformation like this, and then you perform Suzuki-Trotter decomposition for this unitary evolution, and these are the operators in this form. So you can write the circuit which is shown here. So these are two-component systems, so you can easily transform this to two layers. So one layer for one component, the other layer for the other component, then you couple the two layers, which is your U up-down interaction. So this is shown here. This is this 1, 2, 3, 4, 1, 2, 3, 4 sites for the upper layer, and this 1, 2, 3, 4 for the lower layer. And then this B's are the coupling, these are the U up-down terms. In A's are the hopping and the nearest neighbor interaction terms. Then we can actually show that similar physics can be obtained or observed in this quantum computing experiment. So the left side is the exact or classical numerical simulation for this Hubbard model type setup. So here also you can see that this P up-down is formed in the time dynamics, in the Quench dynamics, and it is much stable when delta is small. And here also this resonance condition is matched, so P up-down probability is maximum at the resonance at 10. And on the right side, this is the quantum computing results. You can see that this green one is the exact result. This triangles are the noisy data, and this has been error mitigated with different error mitigation techniques. So you can see that very nice signature of this resonance condition and also the pair formation. Now one interesting thing here is that when you increase delta from 0 to 1, so the pair formation increases and pair formation decreases, and at delta equal to 1, both these probabilities are finite, equal, and then when delta increases further, this pair formation probability decreases. Okay, so this is also seen here. And this is the time evolution, again from the data from this IBM-Q simulation. You can see that a pair is being formed on this central, on this side, first side, and the extra particle moves apart. So now the question is, how stable are these doublons? So then to understand this, you start an initial state with one Doublon already formed and one extra particle sitting here, then you will see that when I increase, if I go along with the time, if I time evolve this, so these two possible states are there, of equal energy, because at the resonance, this has same energy as this. But we'll show here that, 1 minute, this is the last slide. So we will show that when delta is 0.2, this Doublon formation probability is maximum. Then as you go on increasing delta at 1, it is around 0.5. But you go further along the delta line, you will see that when delta increases further, this probability increases. So that means from large to small, and then it increases further, which can be seen here. This is a TVD simulation. The probability of Doublon formation decreases, reaches a minimum at delta equal to 1, then it further increases. Same thing can be seen from the exact data, but from the quantum computing experiment, although we see some features, but it is not very solid here because of the noisy qubits available free to us by IBM. Maybe if one gets some very good quality qubits, then one can see this nice feature. Okay, so in summary, non-local particles don't form local bound state in their quantum walk. But if you take two-component system which favors a stable Doublon due to two different competing interaction, and one can see these signatures of Doublons in a quantum computing experiment. Although, as I said, one can see this in two-component BEC experiment in optical lattice. So these are the people who are involved in this work. Thank you very much for your attention.
Thank you, Tapan. What a nice talk.